as Arjit said, this is a very diverse meeting and we are a very diverse group. And one of the interests of me personally and broadly of many people in the group is modeling disease in a large sense, a broad sense. And in fact, we have a VI-funded project called the IMAC Center for Disease Modeling, which was initiated by Setabro and Gautam originally. So Gautam Menon is our former colleague, was now at Ashoka University, but he had one foot here when he started out. The work that I'm talking about is mainly done by Chandrani, who's a PhD student who will be submitting soon. And Dr. Umar Ram is an OB-GYN at Sitapati Clinic and Hospital, Chennai. And the data basically came from her group, and she was involved throughout in telling us what to do and what the clinical relevance is and so on. And Lilavati was a quasi-advisor, I would say, to Chandrani, and I would say also to me. Anyway, so this is kind of a very new area for us. But many of you would have had babies and many of you would not have. So, and even if you did, you might have seen ultrasound images and so on. So let's just quickly overview what is happening here. So fetal development starts at fertilization, and that occurs within a day or so of ovulation, if it occurs. But we normally measure gestational age from the beginning of the last menstrual period, LMP, and actually determining the gestational age accurately is a problem in itself. And since one of Himanshu's students is here, I guess that's something the Garbini project has been working on lately. But for our purposes, we are assuming that, and in this particular data set, the LMPs are kind of well remembered, but clinically it can often be a problem. It's not terribly reliable measure. So conventionally, it's assumed that gestational age is 14 plus fertilization age, 14 days. But that's not quite exact. And after fertilization, typically the fetus develops for about 38 weeks from ovulation, which is 40 weeks from LMP. So 40 weeks is regarded as term, and anything from 37 weeks above is regarded as, term. Birth before 37 is regarded as preterm. If GA is more than 41 or 42 weeks, the baby is regarded as overdue, and often induction is offered. Otherwise, there can be complications. So that's a quick summary. And the clinical questions that an OB-GYN typically might be interested in is, for example, is the fetus developing normally in some sense? So people do ultrasounds and other tests to measure the state of the fetus, which we'll come to. Are there possible complications and is some intervention required? This can be both for the fetus and also for the mother. For example, preeclampsia is a serious health risk so we'll come to that maybe. What is the likely birth weight? So this is something that we will focus on here. Healthy birth weight is regarded as something for full term as anything above 2.2, 2.3 is regarded as okay typically. It could be as high as 3.5. If it's much more than that, it's regarded as heavy. But the terms you're using is SGA and LGA, small for gestational age and large for gestational age, meaning it depends on at what point the baby was born. So these are things that doctors are concerned about. And we cannot measure the fetal weight in utero because there's no way to do it. If we could, then we could maybe extrapolate where the birth weight will be. But we can measure fetal linear dimensions, and this is routinely done by ultrasound measurements. So ultrasound basically sells ultrasonic waves, and you've probably all seen pictures like this. These days you get much better ultrasound images. These are 4 examples of ultrasound measurements. This first one is, and this is at 12 weeks. This is CRL, crown rump length, which is not part of the data we are using. It's often measured basically to estimate the gestational age. If it is done at 12 weeks, you can, and you are not sure of the LMP, this can be used. So this is these yellow dots mark what's being measured. This abdominal circumference, which is this, and this is femur length, which is these dots, and this shows both the biparietal diameter and the head circumference. So the biparietal diameter is basically one side of the head to the other, and the head circumference is the round thing. And people also measure the occipital frontal diameter, which is up here. but that's again something we won't use here. The 4 measurements that we are using in this work is biparietal diameter, abdominal circumference, head circumference, and femur length. Now, all of these measurements have growth standards from various organizations such as WHO and NICHD in the US, and a group called Intergrowth. All of these have been updated or published originally, but updated in the last 10 years or so. So this is from 2017. What is a standard? It is just an observation in a population of where these things tend to fall. So the 50th percentile is the red line, and the 95th percentile is the dotted green line, 99th percentile is the solid black line. Basically, if you fall outside the 10th or 90th percentiles, they might conclude that you're not growing appropriately. For example, NICHD has similar standards, and Intergrowth provides these really weird formulas instead of standards. And being new to the field, we were scratching our heads wondering where these things could have come from. Essentially, it's probably some computer fit, but if you just look at these curves, all of them, they are basically sigmoids. They, start off a little slowly, maybe become almost linear, and then taper off towards the end. That's what it looks like. And so our question was, can we, instead of fitting it via some regression model, can we model the growth via some well-motivated growth model? And then can we learn the parameters of the growth early in gestation to predict the eventual birth rate? And then if a fetus is not growing according to a model, is there any clinical implication? And so this is a quick outline of what we did here. And the model we used is the Gompertz model, which some of you would be familiar with. It's a model of constrained growth that was originally developed for populations in the 19th century, but it's been applied to a whole bunch of other areas. The basic idea is that you are growing at a rate R, which itself is decaying exponentially. And the solution for this looks like this, which this is how it's often written in the literature, but we like to reparameterize it as this, which also is used in literature, and it has advantages. So essentially, this is the growth formula, and the interpretations of this is that C is the same C as here. It is the rate of retardation of the growth rate. T naught is an inflection time, meaning this is when it changes from concave up to convex up. And it is an overall scale parameter. And so this is meant for a system like a population, or it has been used for tunicers and so on. It has been actually used previously for fetal weight, and by these authors in the 1990s. Incidentally, this journal no longer exists, and online archives don't exist, though it was a venerable journal at its time. So we had some trouble getting the reprints, but they're interesting to read. So they model fetal weight in these, or fetal volume, which is like linearly related. How do you do that? So they basically used aborted fetuses, and not even from the same time point, but from historical data. So it's pooled data dating back to 1909, and they did show that the fetal volume was modeled very well from 15 days post-conception till term, and in fact they improved it in the later paper. And they had some arguments for why the Gompertz formula work, and they modeled volume as an ellipsoid. Now we don't have, we could in principle measure the fetal volume maybe from the ultrasounds, but that's kind of complicated to do. Instead, if you're going to model it as an ellipsoid, and if you have 3 ellipsoid axes with the same T naught and C, then the ellipsoid volume also has the same formula, which you can quickly check from the formula. So we used the Gompertz formula for the ultrasound measurements themselves, which are linear measurements. We are using basically this idea. So this is the cohort that we had, 3,000 something women at this hospital in this time period. For whom all these ultrasound biometries were available. And we required all of these available with a minimum of 3 sets required. The first set at less than or equal to 15 weeks, because many of these patients came from some other hospital or something and they were missing data. So, and then we consider only singleton pregnancies, no twins and stuff. And after all these filters and quality control, we have 817 women. And if we want a second ultrasound at less than 25 weeks, then we have 774 women finally. So these are the characteristics which I'll skip, but it's a fairly normal cohort. And the first observation is that the Gompertz model fits the cetapathy cohort quite well. And I would say basically, so I didn't emphasize this, but if you go back to the Gompertz formula, it turns out that we can estimate C and T naught for each parameter globally speaking. I mean, using the each value fits for a given biometry, we need to estimate it only for the entire population, and E unknown can be used to fit an individual fetus. So that's the that's what we ended up doing here. So in all these cases, the colors indicate, so the dots are actual ultrasound measurements, and the colored lines are the best fit to those measurements. In this case, it's the worst 5 fits. Even the rest ones, as you can see, are not terrible, but they are pretty good. But the best ones are pretty much on the dot, and most of the average ones are on the dot. So in all these cases, T naught and C are constant, and only A is actually fitted. So A is the scale parameter. So what this means is that if it's a bad fit, maybe C was actually wrong. We should be using a different C, or maybe it's a different shape altogether. Maybe it's not growing according to Gompertz curve. So these are the parameters that we get when we fit it, and we get a different T naught and C for each of these, but it's not terribly different. It's in the same ballpark. And we get a range of A's, which is basically the representative of the cohort that we use. So we find that the fetuses that fit poorly, which we measure as the mean squared error to that curve here. Given this curve, you can calculate what's the mean squared error of the individual dots to the curve. And we look at the worst 10% versus the rest and look at neonatal complications. And we find that there is a significant difference in the well-fitting and the poorly fitting fetuses. And the particular complication that comes up notably is IUGR/SGA. IUGR is intrauterine growth retardation, which can often be diagnosed during pregnancy, especially via ultrasound or something else. And SGA is the outcome, it's small for gestation rate. LGA also shows a significant difference, and then some of the other complications are only showing, but this is partly because the data set is kind of unbalanced. The most tests for fits were good. So here is the main part of the talk, which is predicting the birth weight from the ultrasound measurements. And basically what we did is for each of the 4 measurements, abdominal circumference, head circumference, femur length, and biparietal diameter, we estimate E from the Gompertz formula and the available ultrasounds. That is basically, we just fit it. And so we might have, we do this either with the first 2 ultrasounds or with the complete set of 3 ultrasounds. And then from that, we estimate the final biometry at term, what we predict it would be at term. So just to backtrack, there are literature formulas for this already for estimating the birth weight from the ultrasound. And the most commonly used one is due to a guy called Havelock, and it goes back to the 80s. And a lot of ultrasound machines actually come equipped with it. So it's done routinely. But the drawback is that they expect the ultrasound measurement to be available within a few days of delivery. That is, the published papers that benchmark this have ultrasounds taken within a week before delivery. And that is not routinely done at all. It's only done when there's some kind of complication. So we are instead trying to do this with the routinely done ultrasounds. And so A24 and A25 here basically indicate the value of this parameter based on data till 24 weeks or till 35 weeks. And so we are basically using a leave one out method here where you train on n-1 samples and test on the single sample so that we are never actually predicting on the data you have. And then finally put it together and get a trained model which gives you this regression formula in terms of, so we used various parameters in this. These things are estimated A for BPD, A for HC, A for FL, and so on. These are the scales of those grids. But we also used the actual values of BBT and so on, which correspond to the predicted values at the end. So this is the coefficient and this is the predicted value. We also used considered quadratic and other combinations, but it turns out that this is what comes out as a formula. And we also considered maternal parameters, which caused a small but not great improvement. So we are still interested in seeing how it can be improved. But based on what we have so far, it seems we do much better than the standard birth weight formulas. So I mentioned the Hadlock formula earlier. I should also mention that Intergrowth itself has these, so those formulas that I showed earlier. You could use them to predict the final biometry. So all of these formulas, Intergrowth, Hadlock, and Shepard, estimated fetal weight formulas, use ultrasound parameters to predict the birth weight. And their published benchmarks use ultrasound parameters that were taken within a week of before pregnancy, before delivery. So instead, we use those formulas with our predicted final biometries from the Gompertz formula, as well as with the final predicted biometries from, if we use our biometries, these all do reasonably well in terms of mean absolute percentage error. Gompertz is like 10, which doctors would consider good, and MAP is less than 10 for Shepard, but we do less than 8% of MAP. So it looks like our regression formula combined with our prediction of the final biometries is giving an error as less than 8%. So that was, we thought, pretty good, and we sent it off, and it has rattled around a couple of journals so far. I think the first one, there was just too much material in the paper, being half of us being physicists and modelers, we didn't know how to write for a medical journal. The second one has also been sitting on it for a while, but we're hopeful that we'll see the light of day at some point. Right, so this is our birth weight prediction, which is the main part of it. This is not visual, the heat map of the error percentage. Essentially, this is our thing, and 71% of our patients fall within 10% error. 61% fall within 8% error. So that's how to read this, and none of the others basically come close in terms of this. Right, and we had an independent validation cohort which came to us. This is slightly later data from South India. It's a cohort size of 365 patients, and we get an MAP of 8.4% in predicting birth weight in this cohort. Then we wondered, can we use the Gompertz model as a plausible basis for growth standards instead of those complicated formulas that Intergrowth uses, or the charts that WHO and NICHD give? The way you would use those charts is that you place your actual measurement on the chart and see in terms of these percentiles, where does it fall. Instead, what if you could use the Gompertz formula and use that scale parameter A to the, so here, these are fits of our in-house data with Intergrowth, and we have a similar curve with the WHO standards. You can see that it depends on your prior biases, I guess, but both seem to fit pretty well. But the Intergrowth function as given, seems to level off extremely sharply towards the end, which seems a little bit unrealistic, both looking at the data itself and by what you might expect. In fact, if you extrapolate these two functions, it actually starts falling, which is nonsense, but the intergrowth rules, you don't use it for more than 40 weeks. So what we try doing is fitting our Gilbert's formula to the published intergrowth formulas. And in these three cases, actually, we get a very close fit. So why not to just use this kind of formula as a growth standard? It's even better if you compare with the WHO curves. So that's one better rule that we have, but it's actually it wouldn't be easy for to change international practice in this way, but it's just something we're throwing out there. So the other thing I have to say is that intergrowth was, in particular, there's then a cohort of international pregnant women with very stringent health indicators like comorbidities and the minimum height of 5 feet, I think, and the minimum weight of so much, maximum weight of so much. And it was heavily biased towards Caucasian women. And if you talk to the authors of that, saying that they're basically excluding huge numbers of people in the world, they argued that these are the prescriptions for healthy growth. And so basically, everyone who is less than 5 feet must be stunted. It can't be naturally that kind of thing. So whereas the WHO and the NICHT seem to accept that there are genuine ratio differences and geographic differences in these numbers. But the interesting thing is that we, despite being from a city in the developing world, it's mostly urban women, we do fit intergrowth pretty well. So that's basically the summary of this talk. The Gompertz formula basically fits the growth of our cohort, and these two seem to be nearly universal, and they are basically fitting individual fetuses only by A and not by the other two parameters, which is helpful. And we find that outliers seem to be associated with neonatal complications, and we can learn this parameter A in particular, predict final biometries, predict the fetal weight. We do better than standard formulas, even though we are not using very late term ultrasound. And we are fitting standard, growth standard formulas using the Gompertz formula pretty accurately. So where do we go from here? As I said, growth standards are one size fit all, but maybe we can use Gompertz as a personalized formula. And maybe we should, all of these standards are based on cohorts with healthy parameters, and that includes the Citadel cohort because it's a private hospital in a reasonably affluent city. If we study populations from, let's say, rural India or from, populations with maternal complications, does it work? Is there a change in T0 and C? That's something we can look at. And we saw, as I said, some improvement in including maternal parameters such as maternal BMI and blood sugar, gestational diabetes. Some of those things did improve it from like 7.8 MAP to like 7.7 or 7.6. And we think it would perhaps be further improved, maybe using improved machine learning models, whatever. And just to conclude, there are some other things that we have been doing along the same lines. With Pennaswamy Saravanan's group in Warwick, we've been working on various machines. He's a professor of endocrinology and obstetrics and gynecology. And he's particularly interested in both gestational diabetes and postpartum diabetes. So these are a couple of things that we did with him. And very recently, we've started working on predicting preeclampsia risk in early pregnancy using some Doppler data that Uma has. And that's something, as I said, internationally, preeclampsia is a major cause of maternal mortality. And there was a very interesting talk by Bhaskar Tilaknathan last year at a meeting at ICTS we organized about how preeclampsia, preterm death, stillbirth, IUGR, RL, basically not diseases in themselves, but symptoms of placental dysfunction. And that was like the theme of his talk. But he talked about how they have improved prediction of preeclampsia by using a sort of machine learning approach instead of a checklist approach. And not only have they improved outcomes in the hospitals that have implemented this, but they have eliminated racial differences which exist in other hospitals, like Black women, South Asian women are much more likely to get preeclampsia. But when their checklist was, when their formula was used, these differences went away. So there's tremendous scope in, improving all of these things. And that's something we want to be working on going forward. Thank you very much. Harish.
Nice talk, Rahul. Just if you divided the post-birth into male and female, does it make a difference? Because I would have thought there is a difference in the weight.
Very valid question. But in India, we legally not allowed post-birth. Yes, but we are interested in outcomes, right? So during pregnancy, we cannot know the gender. Of course, if we do it, and we have considered doing it, and a lot of the medical community actually really wants to overturn this law because this is not the way to handle female feticide by cutting off valuable information from the clinician. But that's what we are stuck with. So it is something that we could do as a, I guess, research question, but in India as of now, it is kind of useless. So that's
right. So very interesting. You did mention about the population differences that might exist.
Yes.
In terms of socioeconomic differences that would play a role in defining this, do you think considering the parameters from mother based on her, for example, what kind of nutrition that she's getting would have an effect on this?
I think it definitely would. We didn't have that kind of data here. I think the Garbini project is collecting that kind of data in their cohort, which is based in, I think, Gurgaon and, NCR area. But I haven't talked to them about that. But yes, it should have an effect on.
So typically the interventions would be required.
Yes. Hopefully first or early second semester. Yeah.
Semesters. And maybe, I don't know if I read it correctly, that as you went before early pregnancy, the error rates were. So.
Let's go back. Sorry, you're talking about the predictions? Yeah, so if we predict, using 24-week data, the error rate is higher, and with 35-week data, the error rate is lower. That was what you were saying? Yeah. Yes, we do want the interventions to be done earlier, but even 35-week is not useless because, yes, but if we can really predict at 24-week that the fetus is not growing normally, then they can see what's. So a simple example for preeclampsia, if there is a risk, they just give aspirin. But they don't do it routinely because there can be other issues with aspirin. But it does help. But for abnormal growth, they might look at the maternal nutrition. They might. So I'm not an expert in that side of it, but it's something that they want to. Right. Definitely. So there's always a trade-off in any intervention. So here. Yes.
No, I have a very similar question to what he asked. Like, take into account the mother's properties, like her BMI, and if she had that would actually.
Yes. And yes. It did not hardly improve our results, but maybe we didn't try hard enough. So we will look at that and other things.
Hey, Rahul, interesting talk. So the question I had is the last but one slide. It's related to the previous question. So you said that all the different ones had similar T0 and other things. So if you look at the different populations, let's say Western populations versus Indian populations, should we think about what would be the main difference? Would it be mainly at the starting point, like A? So one population might be scaled up and another will be scaled down, and then the growth is all similar, or how should we think about A for different populations?
That's a good question. And the interesting thing is, if you look at T0, so this is our cohort, which is Chennai. This is integrate, which is mainly developed world. We have basically fit the benefits formula to their formula. It's the best fit. And if you look at T0 for head circumference and biparietal diameter, it's pretty similar. Whereas for abdominal circumference, T naught is much later for the intergrowth formula, and female length also is a bit later. I don't know what that means really. And C's are also sort of in this ballpark, but again, for abdominal circumference, it looks like a bit of a mismatch. If you look at A, the real, it's actually higher for its circumference in intergrowth compared to Zeta-50, but Zeta-50 is lower for abdominal circumference. Now, is that related to and the other two are kind of similar. Is that related to nutritional standards? And if you compare with WHO also, our abdominal circumference is lower, but not as much as with intergrowth. So we haven't really looked at all this. But these are things that, one.
So one quick follow-up comment is that the fetal weight that is based on all of these using Hadlock or other models, if you fit this kind of a comfort model, I guess that will be like an aggregate of all of this together into a single.
Right. What we did in that slide is we predicted the final ultrasound parameters using the Roberts model, and then used the birth weight formula of intergrowth and so on. That's not the ultrasound formula, it's a different formula. They have birth weight prediction formulas, so we used those. And actually for Hadlock and Shepherd, it's not too bad, but we do measurably better.
So I don't think it.
Okay.